My name's Alistair Beresford. I'm the current head of department here in the computer science department. So I'm very pleased to welcome you all to this year's Wheeler Lecture, our annual series of distinguished lectures named after David Wheeler, who was an early pioneer in computer science and who made significant contributions across many of the areas of computer science, from programming to system design, as well as data compression and encryption. So as some of you will know, David worked on the original EDSAC computer, one of the world's first program-stored computers that was built here in Cambridge and operated in the 1940s and 1950s. David's career was spent here in Cambridge teaching and working alongside many of us, and was one of the first computer scientists to be elected a Fellow of the Royal Society in 1981. And whilst David is no longer with us, I'm very pleased that Joyce Wheeler is here with us today. And she too was an early user of computing technology and worked on the EDSAC computer from 1954 to 1958, I think, correctly. So I'm very pleased that she can join us as well. And as you know from the talk advert, we've got Peyton Jones, who's come here to give the Wheeler Lecture this year. He studied maths and electrical sciences here in Cambridge, followed by a diploma in computer science in this department afterwards. After that, Simon worked in industry before returning to academia, first as a lecturer at UCL, and then as a professor in Glasgow. Simon moved from Glasgow back to Cambridge for a position at Microsoft Research in 1998, and in 2021 joined Epic Games as an engineering fellow. Simon's main research interest is in functional programming languages, their implementation, and their application. He is particularly motivated by direct application of principal theory to practical program language design and implementation. And Simon has made many significant contributions over the course of his career, including major contributions to the Haskell programming language and lead developer of the Glasgow Haskell compiler, as co-creator of the C++ language, as well as significant contributions to computer science education in the UK and beyond, both through Computing at Schools initiative, as well as chair of the National Centre for Computing Education. He holds 4 honorary doctorates, including those from the Universities of Glasgow and Kent. He's a Fellow of the ACM in 2004, a Fellow of the Royal Society in 2016, a Distinguished Fellow of the British Computing Society in 2017, and awarded an OBE in 2022 for services to education and computer science. He's also a distinguished visitor here in our department. So Simon is well known for his kindness, for his generosity, as well as his brilliant mind. And he's also well known for giving talks on how to give talks. So I'm hopeful that today's talk will be particularly good. Over to you, Simon.
Well, good afternoon. It is an honour to be invited to give the Wheeler Lecture because David was one of my lecturers when I did the diploma, which I think he had a hand in creating. I think he created it. At that time, University of Cambridge didn't think computer science was worth a degree. It was a sort of, somewhat grudgingly, they let you get a diploma in computer science. So I started computer science with David. 1979 to 80 was the time. And this is his face, but I never really saw his face. This is really all I saw. So in fact, he was in the habit of giving lectures he would walk into the room, we would see this very briefly, and then he would walk up to the board and he would talk very quietly while scribbling. I still don't really know what he lectured me about. I think it was arithmetic, finer points of floating point arithmetic. But for us, we were just thrilled to be in the same room as the person who had invented the subroutine. We breathed the same air. We were invigorated. And it's a great honour, Joyce, to have you in the room as well. I didn't know this was going to happen. I'm very pleased to meet you for the first time. We had a lovely lunch together. So thank you, David. And he actually wrote rather less than that, I have to say. Now, and so to Epic and to Verse. Oh, by the way, I should say, let's get to that in a second. Let's see. Here, do you want to just switch some of these lights down? I'm sure that some of you will have had the experience of you're at a party and you walked up to somebody and they say, what do you do? And you say, I work for Microsoft and I'm a computer scientist and I'm interested in functional programming languages and category theory. And a sort of panicked look comes into their eyes and they feel an urgent need to get another drink. But nowadays I say, I work for Epic Games. And they say, ooh, that sounds interesting. And off we go. So it's pretty exciting to work for a company that does this kind of thing. This is not one of those films that was rendered, at 1.5 hours per frame and put together. This was actually rendered in real time on a Sony PlayStation. The Unreal Engine, which is the graphics thing and the physics engine that does all this, is a pretty impressive piece of work. And I enjoy working for the company that makes it, though I have nothing to do with it and can claim no credit at all. But what the key thing about Epic Games, why am I working for Epic Games, is because of this man, Tim Sweeney. Now, he is the author of that software, right? He is the original implementer of the Unreal Engine. He's an awesome C++ programmer, but he also has built an extremely successful games company on the back of it. And he is my immediate boss. He's really an uber geek, you should think of Tim Sweeney. He is the sort of Bill Gates of Epic, and he has been thinking about programming language design and implementation for about 20 years, sort of in spare moments between. Plan is that to sort of segue from a games company to games are places where people play, but then increasingly they socialize with each other, and then they sort of hang out together and exchange stuff, and that, before you know it, turns into the metaverse. And so Tim was talking about the metaverse way before Meta was, right? He's been giving talks about this for at least a decade, probably more. So for Tim, this sort of metaverse idea is a kind of shared virtual reality in which people can, live and move and have their being and interact with each other and exchange things of value. That is, make businesses in the metaverse. So the way he describes it as a corporate and an open economy without a corporate overlord. I think it's a bit more like the high street or the high street and makes it a sensible place and it has some rules that means you can't steal from each other and so forth. That's the sort of the setup that he has in mind, right? So he sees it as being a sort of platform where other people, third parties, can create things that are of value and share them with each other. And so if they're going to create things independently, that places pretty strong requirements on the programming model, right? It has to be more than a collection of separate little apps that you can run in separate silos. They'll have to interact with each other, and that's quite tricky, as you will know. So it needs to be sort of pervasively open standardy. So this is Tim's sort of big picture. Now, in doing this, he wants to program all this in a new programming language, which is called Verse, right? We don't really need a new language. We could use Python or Lua, as Roblox does, for example. But when I speak to Tim, it very much reminds me of how I felt in 1979 when I first learnt about functional programming from Arthur Norman. And the light dawned, and I thought, this is how programming should be. And I didn't sort of worry too much about whether it would be useful, because for a long time, functional programming, you couldn't do I/O, for example. I just thought, this feels so right. I think Tim's sort of fundamental story here is he wants to think afresh about the entire enterprise of programming, and he's taking the opportunity to do so. So there are a lot of requirements here about that we want to, write programs that will be written by millions of programmers who don't know each other and run by billions of users who definitely don't know each other. It's got to be really transactional for all of these side-effecting things in games that interact with each other and has very strong interop guarantees. And he also, by the way, wants it to be learnable as a first language right the way up to hardcore developers. This is a pretty ambitious story, right? And who knows whether we'll do it all or when we'll do it all. But I have to say, it's pretty exciting being part of this wild ride. And rather than being a sort of odd researcher who has a sort of glint in their eye in a corner of a company, this is the chief executive and managing director of the company who is, he's the one with the glowing eyes. And that's actually quite exciting and a lot of fun. So here's the plan then. We're going to, a version of Verse is already shipping. We call it Shipverse internally, and it's part of something called Unreal Engine for Fortnite, which allows third parties to develop games in the sort of Fortnite world. They make little islands in which people can interact. And the idea is that then if your game on your island is successful, well, you get revenue from it. So it's meant to be a this is a sort of, if you like, a prototype of the metaverse, but a rather gamesy-oriented prototype of the metaverse. So something is shipping. Here's the URL. Here's what the web page looks like. Meanwhile, we are running what turns out to be a research project that I will tell you about, which we're calling Maxverse. And this is the glorious vision that we're trying to mine out of Tim's head what he's been thinking about. And the idea is that though we've launched Shipverse like a rocket into the sky and it's on its way to Mars, and we are meanwhile designing the sort of Uber version of this, Maxverse, which we're going to launch and meet in orbit, and it's all going to be, Shipverse will turn into Maxverse. That's the idea. Right? But it's also quite exciting. It's very different to working in the university department. So let's see. So Tim then has been thinking all these thoughts for a long time in the back of his mind about functional logic programming, concurrency, and transactions, and so forth. And our job is to suck this out of his brain, right? This is sort of me and Stephanie and Kuhn and so forth. This is the project I'm going to tell you about. Our job is to take all these actually quite inspiring thoughts that he's been having and somehow make sense of them in a way that the programming languages community and compiler writers and so forth can make sense of. That's the idea. So I'm going to tell you about the progress that we made. We made a start on this. There's quite a lot more that's still in Tim's brain that we haven't sucked out yet, but we're working on it. Okay? So I'm going to try to give you a little picture about what the bit of verse that I understand so far looks like. Please do ask questions as we go in a sort of interjectory kind of way. I'll repeat them back so that people online can hear them. But it'd be more fun if I feel you're sort of somehow listening to me rather than just sitting like bread puddings after lunch. Because I'm not going to go to sleep, but I really don't want you to either. Okay? So please do me that honour. Will that be okay? Okay, yes, John.
Hi, have you ever used Lambda Moo back 40 years ago?
Did I ever use Lambda Moo? No.
Okay, so there's a Lisp-based multi-user Dungeons & Dragons game which people could play and interact and reprogram. So it was Lisp, of course, which was a terrible design mistake, but it's worth a look historically because it has a few of the ideas that you're talking about.
Okay. All right, Lambda Moo. Not Lambda Moo. No. Okay, are we ready? Oh, sorry. What happens when you take the spaghetti is we pull on one of these strands. Every conversation we have with Tim, we think we've got a limited topic, and the whole lot lands up in our lap again. So it's repeated exercise here. I forgot about that. Okay, so here's a little picture about what verse is. Verse is a functional logic language. I'm used to functional programming. This is functional logic programming. I'm going to show you what I mean. Silo within the programming languages community. There's quite a lot of dense literature, but it's sort of somehow insulated from the rest of the PL community. I don't know why that has happened. Some kind of funny cultural thing. I think it's a shame, but we're aiming to fix that. So it is a declarative language in the sense that a variable, if you have a variable called x, it denotes a value. It does not denote a box that contains a value which is mutated over time. Yes, there are side effects as well, and then we do have boxes, but that's not the primary computation model. It's also a lenient language, but it's not a strict language. It's neither call by value. And it has an effect system that I shan't show you about, so I won't have time. Okay? That's a little, very 100,000-foot sketch. So, of course, the source language, verse, is a big language. I put big, rich language. When I worked for Microsoft, I learned that rich is always code for extremely baroque and complicated and ill-documented. We hope to make rich short for it have its more conventional meaning of something that is exciting and full of depth and meaning, but in a rigorously grounded, elegant way. But we'll see. And we're trying to give semantics to the big source language in a very traditional way by identifying a smaller core language that I'll usually write in yellow boxes, which is going to be core verse, and we're going to try to desugar source verse into core verse, give a precise semantics to core verse. That's the general plan. So you might think it's very like, if the source language is like Haskell, then core verse is like the lambda calculus into which we translate it. That's the general plan. So that's our notation. So here we go. Here is a quick bit of conventional bits about verse. What is this? So verse is a fairly ordinary functional language. It has integers, 3, and you can add them or multiply them. It has tuples, which are also called arrays, so they don't have to have, they can have elements of various types. So here, and they're written in round parentheses, and they can be nested, of course. And you can pick elements out first, and you can index them. So here, this is what makes it unlike a Haskell tuple. A squared bracket 7 means A should be a tuple stroke array. Just take the 7th element, okay? So that's pretty straightforward. Then bindings, which would be written with a let in Haskell or ML, are just written with colon equals in verse. So x colon equals 3 means bring x into scope and bind it to 3. Yes, please?
So you said 7 elements. So you start
Louder, please.
You start indexing by 1, because you said the 7th element.
Oh, the 7th element of A. Yes? Oh, but it may be the 6th element. I don't know. Maybe it's the 8th element. Yes. Yes. All right. All right. All right. Peace. Peace. Zero indexing. Thank you. Not going to get away with anything today, am I? Yeah.
So you said like arrays can have elements of tuples can have elements of different
Yes.
sizes.
Yes.
Then are they also like dynamically sized?
So are tuples dynamically sized? Yes. So when you build a tuple, it has some size. Right, and but when you say dynamic size, you mean that you're appealing to some notion of a static type system, right? And I haven't told you about the static type system, but I will, but probably rather briefly, and it's a rather unusual bit of verse. Yeah, okay. All right, so here's let definition. So this it brings x into scope and binds it to 3, and then returns. Then semicolon means this is like let x equal 3 in x plus x. This expression returns the value x plus x. You can define functions in a very conventional way by pattern matching, well, or by putting arguments on the left. And so this is a definition here. After the semicolon is a call of the function. So the definition goes as far as the semicolon. The after the semicolon is a call, right? And you can also use lambdas, right, if you want. So you could say f, or f colon equals, and then a lambda. And the lambda in verse is written with a double arrow, equals greater than. Okay? So far so good. Nothing unusual here. Now, and so then, of course, there's also conditionals, and there's also recursion. So putting it all together, you can define a factorial function in just the way you'd expect. No big deal, right? Okay. So what is special about functional logic languages? Okay, so this is where we get out of functional programming. I think it's two things. One is existentials and equations, and the second is choice. Okay? So here's first existentials and equations. Now, so in Haskell we'd write let. In source verse we'd write colon equals, as I've just shown you. But the colon equals is short for this yellow thing at the bottom, in which I split the colon equals into 2 bits. Exists x, which brings x into scope, but does not give it a value. And this equational constraint, x equals the pair, 3 times 4, 4 times 4, which constrains the value of x. That's the way to think of it. 1, I bring x into scope with an existential. 2, I constrain x's value with an equation. So I've split the definition into 2. Does that make sense? Now let me give you a couple more examples of doing that. So the one on the top left here says, I'm bringing x, y, and z into scope, not telling you anything about them yet. Then I constrain x to be equal to the pair y, z. That just says that x is a pair. Its first component is y, second component is z. But I haven't told you what y and z are yet. And then I constrain y to be 3 times 3 and z to be 4 times 4. Does that make sense? Easy enough, really. So let's see. On the right, this thing on the right shows that these unconstrained, as it were, existentially bound variables are first-class values that can be passed to functions. So here, I'm defining f to be a function that takes, I've written this this yellow core language. We have honest-to-goodness lambda, right, with Greek font, not the double arrow, that's source first. And so here, f is a function that takes a v, and what does it do? Then the body of the function is simply an equation that constrains v to be equal to 3 times 3, 4 times 4, right? Then I can call f passing x, which is as yet unconstrained, and that will constrain x by, because if you just imagine myself doing beta reduction, that will turn into x equals 3 times 3, 4 times 4. Does that make sense? So these unconstrained existential variables are first class, and they can be members of data structures, pass the functions, return to the result, the whole bit. The last thing at the bottom is just to stress that these existentials here can be quite local. This x says it's equal to, well, what? It says exists yz, pair yz. So it says, well, x is a pair whose components are completely unconstrained logical variables. And then you can constrain y and z, perhaps by saying first x is 3 times 3 and second x is 4 times 4. Does that make sense? Right? So I'm hoping that when you look at it, you think, this is unusual, but it's quite obvious what they do when you think about it. Does that make sense? Yeah, anybody? Yeah, please.
What happens if you end up with an inconsistency?
What happens if?
If you end up with an inconsistency, like if you assert x equals something, and then you call f on x, and that f assert that x is equal to...
Oh, what happens if you have contradictory? It's like say x equals 3, x equals 4. Yeah. Very good question. That's when we're going to get to choice. Good. So hold that, and if I don't answer it in the next 5 minutes, tell me. Okay. Now, this slide is just to remark that you'll remember from your days of learning Prolog that you can sort of run programs forward and backwards, and it's the same inverse, right? Here's a swap function that takes an x and y and returns the pair in the other order, and you can call it on some definite values 3 and 4 and it'll swap them, or you can call it on some unconstrained logical variables x and y and constrain the result to be 3, 4, and then x and y will be 4, 3. All right? So usual thing, but this is how it shows up in verse. Now, what does execution mean in this funny existential stuff? Well, as Tim put it to me, I remember him vividly, quite early in one of our early conversations, he said, it's quite simple, Simon. He says, to execute verse programs, you just construct the equations and you solve them, right? Execution is just solving equations. I was thinking, I don't usually get CEOs of multi-billion-dollar companies making statements like that. But here it is, because all we just do is we solve the equations by unification. Here we got x equals y3, x equals 2z, and we unify away, and we discover the solution is x is the pair 2, 3, y is 2, and z is 3. That is, we come up with a substitution for all of the existential variables that makes all of the equations true. That's what solving equations means. Find solutions for the variables in the equations that makes all of the equations true. But it is incomplete, right? Here, I could do it by unification. But if I say exists x equals x squared, now I've got to solve a quadratic equation to solve this. And it's not very hard to construct Fermat's last theorem, and no execution engine is going to be able to solve everything. So this, as an execution mechanism, this is necessarily incomplete. But we're going to put up with that. Just as we put up with that in Haskell, you can write programs that diverge. This is going to get to your question. So this one doesn't go wrong, it just gets stuck. Right? So, it says, I can't execute any further. Yes?
How does it know when to get stuck?
How does it know when to get stuck? Oh, yeah, good question. Well, so I'm going to answer that question before the end, right? Because I want to make precise. What is it? Because, well, let me just tell you about choice and then ask me again, right? So, choice. So, existentials and equations, and now choice. What does choice mean? Well, and so now this is getting to your friend's question on the left there about what happens if you say x equals 3, x equals 4. Well, there may be no solutions to the equations, right? If you say x equals 3, x equals 4, there are no solutions, right? So does that mean the program's gone wrong? No, it just means it's yielded 0 results. So in verse, the natural idea, after you think about this, is going to become, of course this is the right thing to do. An expression can yield multiple results. In Haskell, an expression yields 1 result. In verse, an expression can yield 0 results, 1 result, or many results. So here is the expression 3 vertical bar 4 yields 2 results, 3 and 4. This expression exists x equals 3, 4, x plus 1, successively binds x to 3 and then returns x plus 1, and then binds x to 4 and returns x plus 1. So this whole expression yields 4 and 5. Does that make sense? So there's a sort of natural notion of iteration built in. And of course, if you have multiple bindings like this, then you just get a kind of Cartesian product. We bind x to 3 and then return whatever the rest returns. What does the rest return? We bind y to 99 and return whatever the rest returns. So here we get these 4 pairs returned by this little yellow expression, right? So it's very much like in Haskell we'd write it with a list comprehension like this, or Miranda or KRC or any of those languages. Good? So choice is very, but 0 results is also possible. And 0 results is what happens when you get x equals 3, x equals 4. Yes?
Is the order relevant?
Is the order relevant? I could be paying you. So, yes. Excellent questions, sir.
It's called running the lesson.
Yes. Yes, it does matter. And here is why. And this is, now compared to Curry and Mercury and most other functional logic languages, this is a distinctive feature of verse, is that this construct 4 takes an expression and it takes all the values that it yields. I've spoken about yielding, as it were, in a rather a bit like an iterator in Java or something temporal about that, and it turns into something spatial, right? So for takes an expression, takes all the values that it yields and forms them into an array or tuple. So it's important that they are in order, because I need to know whether I'm going to get the array 3 and then 4, or the array 4 and then 3. So yes, all of so choice is not commutative, for example. Right, so if I change this to 4, 3, different program, different result, different array is produced by this 4, okay? So that is it's deeply built into Verse. It's an early design decision. It has some advantages and disadvantages, but that's the way it is. And it has lots of advantages too. So this is an unusual feature, right? More commonly, the existentials in a Prolog program are always, I think, top level, right? There is a sort of bag of constructed Prolog as far as I remember, but mostly you say, here are some free variables, run the program, and print me out bindings for X, Y, and Z, and then print me out some new bindings, some new solutions, maybe another solution, maybe another solution. But that tends to be a top-level thing. In Verse, it's very encapsulated. You encapsulate it with this for construct, okay? But it does require this ordering thing, okay? All right, yeah.
If you compare choices to comprehensions, you have to, in your paper comprehensive comprehensions, you talk about sorting and aggregation functions on lists. Are there sorting and aggregation functions on the results returned by an expression?
No, there are not sorting and aggregation function on choices. There are on arrays, of course, but the idea is you'd format it to an array and then do something to that. Yeah. So the question was whether you could do sorting and aggregation on the values yielded by an expression directly, but no. No. Yeah.
Are results generated by choice operators first class in a way?
Are results generated by choices first class? No, in the following sense. Here, X is not bound to a kind of multi-value, 3, 4. The way to think of it is X is bound to 3, and then the continuation, the rest is executed, and then X is... So X always denotes a single value, never a choice of values. So it's an excellent question. It's quite deeply built into Verse, this idea. So it's like having the list monad part of the fabric of computation. Yes?
Can you get sort of infinite choice?
Can you get an infinite choice? Yes, you can, actually. Yes. And then if you say 4 of an infinite choice, you'll end up with an infinite array, and the computer will just say... just like a Haskell program where you write an infinite loop.
So this isn't lazy.
It's what?
This wouldn't be lazily.
No, and it's not lazily evaluated. So the 4 is kind of strict. You've got to build the whole array. Let me just tell you about conditionals. And those of you who are of a, shall we say, more mature years will remember Icon. Right? Icon had this idea. So Verse does not have conditionals. It just has a choice. So if E has the semantics that if E returns 1 or more values, you take the then branch. And if it returns no values, you take the else branch. So returning no values, which is also called failure, is not a bad thing. It's just like false. It means you take the else branch. Okay? So greater than, then, is a function of 2 arguments that fails, returns 0 results if x is not bigger than 20. And if x is bigger than 20, it returns, what do you think? X, actually, yes. It returns its left argument. As it turns out, it's just a matter of definition. It could be either way, but greater than returns its left argument. So just as a little exercise, what does 0 less than x less than 20 do? It brackets to the right. When does it succeed? Come on, Cambridge. Yes, it's going to return 0. So if x is between 0 and 20, it'll return 0, and otherwise it'll fail. They're kind of cute, right? Is it amazing? You can write if 0 less than x less than 20, then blah, blah, blah. That's what a mathematician would write. And you can write that in Verse, for what it's worth. Okay, so other cute things, right? You can write, here's an if. Now, does this if have a comma, right? I said comma constructs arrays, or tuples, and so it does. Now, if you've got a tuple of something that fails and something else, what do you think you get? If you try to build an array out of an expression that returns no results and an expression, let's say 3, what tuples would you get? None, right? But there's nothing. So, as it were, tuples are strict in the failure of all of their arguments. They just take Cartesian product. So if either of these fails, the result fails. So this is like an and. Comma here behaves like and. And here, this choice here also behaves a bit like or, right? Because this is going to succeed. This expression is going to succeed if x less than 20 succeeds, or if x bigger than 0, y bigger than 0 succeeds. Remember, succeeds just means returns one or more values. It's just synonymous with that. It's not a special another kind of thing. It just means return one or more values. So it's kind of cute. So in a Boolean context, or a conditional, vertical bar really does behave very much like or, short-circuiting or, incidentally. And you can even say this is kind of also cute, right? But what does this say? This says if x equals 3 or 4, what might that mean? Well, that means that succeeds if x equals 3 or x equals 4. I'll show you some rewrite rules that make that clear. Kind of. So things that you begin to think, oh, I kind of like writing this code. Let's see, indexing, arrays. So this for thing you can use for to construct arrays, but indexing here is done with square brackets, but outside the domain of the array, right? If you have an out-of-bound index, indexing fails, meaning not segfault, not out-of-bounds error, just return 0 results. So this thing here, for I equals 1 is just going to return the array of a's I plus 1, and here this one says index a's, but if I is out of range, return 0. And incidentally, there is a funny scoping rule that I'm not going to lay much emphasis on, which is that in an if you have a binding in the condition part, it scopes over the then part, but not over the else part, because, of course, in the else part, the thing's failed, so you've got no value. Okay? All right. Yes, at the back. Why do I write what? Why do I write an if here? What, you mean if I deleted the f and just wrote x plus 1? Oh, well, no, because I need the if because I want to say if I is out of range, I want to return 0. Right? If I just wrote a of I plus 1, then that would fail. Okay. I'm going to skip this because I think I want to keep moving. In fact, I'm going to skip this as well, but I want to. There's a lot of things we want to talk about. Okay, so this comes back to your question about how do we know what a verse program means? Right, so I think I've convinced you that there's something unusual going on, and we need a way to say, given a particular program, what does it do? And for a long time, the answer has been, well, we have to ask Tim, and that doesn't scale very well. So we need to do something about framing a semantics for this language and get a precise story about what any program might mean. So step one is to define what is this core language into which we can desugar the full glorious language. So here is our core. I'm not going to go through this in great detail. I just want you to see that. Let's see. There's the existential here. We've got fail and choice. Fail is the unit for choice, of course. So fail is the computation that returns no results. We've got choice here. We've got function application that I wrote here. We've got all. I haven't told you about one, but I'm not going to, but it's tied up with if. And then we've got semicolon over here. And on the left of a semicolon, we can have what? An equation or expression. So one of these EQ things is either just another expression, or it's an equation, value equals expression. So there's the equations that I told you were so important. And what are values? Well, values can be a variable, or one of these head normal forms, among which are lambdas. So you can see that the lambda calculus is simply a subset of this. Every lambda program is a verse program. Okay? And it's untyped because I'm going to tell you a bit about the type system, but in order to talk about soundness of the type system and about type checking, we actually need we've got a little language. We need to say, what does it mean, right? How do we say that? Well, there's lots of ways that PL people have thought about explaining what a program means. One is operational semantics. So we say, let's have an abstract machine. It's got a stack, it's got a heap, it's got an expression that you're evaluating or a sequence of instructions, and then you give state transition rules. Here are some from a paper by Peter Sestoff for a functional programming language. This one says, in a heap gamma, if you've got an application E applied to P and a stack S, make a transition to the same heap gamma just the expression E, that'll be the new focus of execution, like the program counter, you should think here, and push P, the argument, onto the stack. And then a whole bunch of rules like this. So it's quite operational, that's why it's called operational semantics. And to do this for verse would mean involving, explicit unification and side effecting things in the heap and backtracking to undo side effects that you've done. So it's quite a bit more complicated. Not very easy when you're talking to a program to say, this is what your program means. And that's what we're after. We really want something, above all, we want something precise, but we'd much prefer to have something we could explain to a programmer. It's a pretty hopeful start, right? When I said an expression returns many results, what I meant was the denotation or meaning of an expression is a set, or to be more precise, a sequence of results. Right, so the meaning function takes an expression and an environment that gives you the values of all the free variables and gives you a sequence of values, W star. Okay, so then fail is nice and easy. It just returns, well, an empty sequence. That's pretty good. What about choice? Well, it returns all the things from the left argument of the choice, followed by all the things from the right. It's a kind of union. An ordered union, yes, it's concatenation, but you can think of it as a kind of union operator. What is an equation? Oh, actually, when you think about it for a bit, I'm not going to linger here, but when you think about it a bit, you realize that Tim said this again. Tim said this. He said, equations just mean intersection. Take the values from the left argument and the values from the right argument, and the values that are in both, that is the intersection, are part of the result, because only then will they be equal. So when you look at this, okay, so choice is union and equals is intersection. Now you think, oh, there's something right going on here. Okay, so existentials, though, are a bit harder, because what do I bind X to? Because usually I'd usually extend the environment with a binding for this value X that is now in scope. But what do I bind it to? I've got nothing to bind it to. So we have plans, we're working on it, but that's definitely work in progress. I'm going to mainly spend my time talking about a third approach to semantics, which is using a rewrite system. So this is really just taking our cue from the lambda calculus. But after all, remember here, verse is a kind of superset of the lambda calculus. How do we give semantics for the lambda calculus? Well, a very popular way to give semantics lambda calculus is with a rewrite system, right? We just say, you just use the beta rule, and maybe each some operations on primitives, and just keep rewriting your program, right? That's pretty simple. Also, very intuitive. Here, in this room, I'm perfectly sure there have been lots of slides that say, this thing rewrites to this, where it's an ML program, right? I'm seeing some nods, yeah? So this is good. Now, so we're all used to this. Here's a little example. The main point about this little example is just, which is a sort of more Haskell-y kind of one, is just that there are many paths through this rewrite thing, right? You can rewrite any expression at any time, anywhere. Of course, if you want to execute with maximum efficiency, you might have a strategy for which rewrite to do first, but it's always valid to do a rewrite anywhere in the term, okay? All right, that's the idea. So here we are then. Rewrite rules can be applied anywhere, anytime, and it's rather important that they all yield the same result, at least if you want to have a deterministic language. And verse is intended to be deterministic. Okay, so somehow, no matter what order you apply your rewrite rules, you should get the same answer. At least you definitely shouldn't be able to rewrite the same program to 3 and also to 7. That would be bad. Okay. These rewrite rules are a good way to explain things to programmers, and they're also great. The other thing that I'm like about rewrite rules is this is what compilers do all the time. They transform programs to programs to programs to programs to programs. Hopefully they're optimizing, but at least they're doing program to program rewrites that preserve meaning and hopefully improve efficiency. All right? So so that's what compilers do. Okay. Now, what about functional logic, though? Because functional logic seems to involve this about existential. When I started this, I was really thinking, maybe this is just not going to work because unification just doesn't feel like the thing's going to fit this paradigm, because I've been so trained into thinking of unification as a kind of side effecty thing, right? But actually, it isn't. Look, we just stole an idea from Zina Ariola, Matthias Verleisen, and John Morace and Martin Dursky and Phil Wadler. This amazing paper, Call by Value Lambda Calculus. If you've not read it, you really should. It's a classic paper, because it has a single key idea that says this was the paper that first showed that you could model call by name, call by need, that is lazy evaluation, not just call by name and call by value. You could model call by need as a term rewriting system in the lambda calculus by adding let. So, as they put it, we're going to augment the term syntax by adding this let bound thing, which sort of reifies the heap, that gamma thing that I showed you in the previous slide of the operational semantic, and makes it part of the term. And that's a very liberating thing to do. And it's what happens inside GHC every day. We're literally doing these rewrites involving lets. So let me just show you an example of how this might play out in verse. So here's a program. X equals this existential, y equals that. So x also equals that existential, and the result is x. So what have I done here? I've rewritten, because I've floated the exist y and exist z, I've floated them out to the top. That seems like a reasonable thing to do. That is a rewrite rule in our verse calculus. Then, having floated it out to the top, I'm going to take this red occurrence of x, and I'm going to replace it by 2 comma y, because after all, x is equal to 2 comma y, so I'll just substitute. So now I've got 2 comma y equals z comma 3, right? Now what? What are you going to do now? Next step? You're going to what? The two pairs are equal to each other, so we can sort of decompose, right? Like this. So 2 must be equal to z, and y must be equal to 3. Bingo, right? That's a little rewrite rule. And now we can do more substitution, and before you know it, then we need a kind of garbage collection rule that says, well, I've got exist x, y, z, x equals this, y equals z, but the result is 2, 3. All of these existentials and equations are now useless. We can just garbage collect them, right? So garbage collection shows up as an actual rewrite rule. So, and you could do these rewrites in other orders, right? It's all confluent. And so I'm just going to give you a very quick sort of video presentation of what the rewrite rules kind of look like. A function. Support. So some of the ones we've seen already, like that tuple decomposition thing here at the top, v1 to vn equals v1 prime to vn prime, decompose it to get a bunch of equations here. If you've got two constants that are not equal to each other, you fail. If they're equal to each other, you return just the constant. And then the substitution rule. Do you remember we had substitution here that if I've got, what have I done here? Y equals 3, and I want to substitute for y. So I replace all the other occurrences of y, like this one and this one. I replace them with 3 down here. Okay? So now I've just got to find a notation for that, and there's standard notation. If I've got some context, and I've got an equation x equals v, then I can rewrite to, I still leave the equation x equals v, but I replace x by v in E, this part to the right, and also in the context. So, simple enough. And then there's a bunch of other rewrite rules that I'm not going to trouble you with, because I want to talk about types. I will just pause just for a moment on choice to say, what happens for choice? So here's an example right at the bottom. X plus y choice z times 2. What should that rewrite to? Well, you can see that I'm going to iterate with this whole expression with y in that place and the whole expression with z in that place. So I want to take the context surrounding the choice and just duplicate it. So here we are. I've got and the context is x plus something times 2, x plus y times 2, x plus z times 2. So the rule looks like take a context around a choice and duplicate the context. This is not new to verse. We didn't invent this. This is absolutely standard in the calculi with choices in it. But it's a simple, elegant, direct rule. In the paper, you'll see that our rule is actually a little bit more complicated. It feels like a carbuncle on the face of a much-loved friend. But we have managed to eliminate the carbuncle. But if you see it in the paper, then you should still have hope. Now, last thing about the rewrite system is that we really want it to be confluent. And now we've got a system of rules that is, here's the rules, all of them. which I show you just to say they fit on one slide. That's all, right? Which is better than it could be, right? It could fit on 2 slides, but still, this is a big system to prove confluent. We would like it to be confluent. And in fact, moreover, it isn't. That's a bit more of a problem, right? It's hard to prove it when it's not true. And it's not true for a very tiresome reason. I'm just going to very quickly show you the tiresome reason. Look at this. Just look at these 2 expressions over here. This is a sort of recursive equation. Exists y. And then I've got 1 comma y. And here I've got x equals a pair and with a lambda in the component, and then x. And if you squint carefully at these 2, you see that they're really the same thing. If you draw them as a graph, they will be the same graph. Because what have we got? We've got 1 comma y at the top here. What is y? Y has a lambda as the first component, a lambda in which the body is 1 comma y. If you draw it as a graph, you see it's the same thing. So these look syntactically different, hence not confluent, but they are semantically identical. So confluence is too strong, right? We don't actually want confluence. If we had confluence, it'd be great. That would be enough. But it's too strong. So what to do? Well, one thing is we can restrict our language a bit. That's what we did in the paper. If you read the paper, you'll see this. Another thing is to take a different and weaker notion called skew confluence, also due to the amazing Zena Areola, and prove skew confluence. And this is what Guy Steele is doing. It was amazing the day that Guy Steele... This is really interesting. Can I help? We delegated proving skew confluence to him, which is a pretty powerful sort of proof engine to delegate to, I tell you. Yes, coming along. Incidentally, Zena says, I'd be interested to, you guys are all very clever. She says, nobody proves confluence anymore, Simon. Right, because it's so 1980s. Right, nowadays we do something with filter models or something. But the thing is that compilers do rewrites, and I don't want my compiler to get stuck in a dead end by rewriting things in the wrong order. So we are stubbornly proving confluence against Zena's advice. But that's an interesting topic for some of you very clever people to educate me about. Okay, now 5 minutes on types and then we'll finish, okay? So I want to just give you a quick flavor about types in verse, but it is also very unusual. So usually a type in Haskell is something different than a term, right? It's a whole different kind of beast. In verse, a type is simply a function that may fail. It's a function that may fail. So int is a function that fails on non-integers and succeeds on integers. And in fact, it's the identity function on integers. Types aren't necessarily identity functions. The absolute value function, which succeeds on integers and returns the positive, the absolute value, is also a type in verse. Right? So it's just a function that can fail. And the idea is that when you say that a function takes an argument of type t, you just mean that the function takes an argument for which t should succeed. That's what. And you can easily define your own types. So here I'm defining a type nat, which is only true of positive integers, or positive or 0. It's a function that takes an x that should be an int and succeeds if x is bigger than or equal to 0. That is the definition of nat. That's all verse knows about nat. It's a perfectly ordinary term definition. Types, it's easy to define rather dependent-looking types. So this one at the top is the function that takes an argument. It checks that it's a pair. How is it checking that it's a pair? Because it's unifying the argument with this pair PQ. That would fail if x wasn't a pair, so good. So it's making sure that x is a pair. And then it's checking that int of p succeeds, and then it's checking that int of q succeeds, and then it's checking that q is bigger than p. And finally, it returns x. So this is a pair of integers in which the first is bigger than the second. Right? So it's very easy to define rather wild types. It's kind of cool. You can see type checking is going to be pretty hard, but hey, Tim never worries about things like that. Let me just tell you about, I can't resist telling you about array. So type constructors are also just functions. So pair is a type constructor. What does it do? It takes 2 types, T1 and T2, and clearly, so pair of T1 and T2 had better be a pair of T1 and T2 is meant to be a type. That is a function. So it takes an argument x, and it checks that x is a pair, and applies T1 to the first component, T2 to the right. And then, of course, it returns the pair y1, y2, because remember, T1 and T2 might not be the identity function. So we're sort of squeezing the input through the pair type to produce a new value. And look at array, the array type constructor. It takes a type, and what does it do? Array of t takes a type and returns a type. What is a type? It's a function that takes an argument x, checks that it's an array, with isArray here, and then what must it do? It must check that all the elements of the array are of type t. How would it do that? Samuel, how will it do that? No, how is it going to check that every element of the array has type t? Anyone? Sorry, I was just teasing you. Apply t to each element of the array, yes. And since t might not be the identity function, what should we do with the results? Form them into an array. So the array of type constructor is the map function. Okay, so this is quite cool, right? The array of type constructor is the term level map function. At this stage, your brain melts and you start. Anyway, so this is what typing in verse is like. So how are we going to type check it? Well, so the type checker is called the verifier. The slogan, as usual, is verified programs don't go wrong. It's okay for the verifier to be stupid and reject too many programs. It's not okay for it to be not clever enough and accept too many programs, right? And so, of course, it's completely undecidable, but it's okay. We can be conservative, and it's more closely related, I think, to checking contracts, static checking of contracts in Scheme, of which there are a couple of papers, than it is to anything else that I've seen. But if this relates to anything else you know about, please tell me afterwards. And this is what we're wrestling with now. So Tim has a verifier, which he implemented in C++, and he's carefully explaining to us, and we're trying to reconstruct it in our heads. It's a lot of fun. So I'm going to finish here just by saying there's a lot more that I haven't told you about that I barely understand. There's mutable state, an effect system, transactions, struct, classes, inheritance, open functions, and a form of overloading. There's a lot going on in verse, but the only way I can make sense of it is by taking it one step at a time, and that's what we're doing. But the truth is we are actually trying to do all this crazy stuff, right, in a real programming language that is already being used by real people, and I hope will get used by a lot more real people. So it's quite a big and ambitious research project, and I think it's quite open as well. We're publishing papers about this, and the only reason we're not publishing more is we're too ashamed of it yet, right? And we haven't got the bandwidth to interact with too many people about it. But it really is meant to be an open research project, and will grow more and more to be one. With all this source code will be open as well. So I would love to sort of interact with more of you about it. Yeah, please. So I'm done now. We can have questions. In a way, if you took an advanced Haskell program, you can make it look. It can be quite tricky to understand, but simple ones are quite easy. So I think it's easy to write simple verse programs in a way that looks pretty much like Python actually, and it's verse left to right flavor. It's more left to rightish than Haskell is, I think. So there is a kind of subset that looks fairly familiar. And that's why there are these colon equalses and semicolons and curly braces. There's a bit of verse that looks quite familiar, and then you realize that there is no glass ceiling. But I think it's a experiment that we're doing is, can we make it so that it is accessible to end users and yet has all this funky stuff? We shall see. We're going to try jolly hard. This because I want people online.
Yes. I wondered what the performance impact of functions as type idea is. Like, does the compiler understand, this is an integer, so we can optimize it as that?
Oh, yeah. So the question is about the performance impact of the type system. Well, so I'd like to be able to say, look, just as in a statically typed language, you can forget about the types once you've verified it. But in fact, you can't, because remember, the types are not necessarily identity functions. So you should think of, but some of them are identity functions and could be statically recognized as such, so we throw them away, right? And the ones that aren't, well, they're just a part of the fabric of the program, like any other. So of course, if you want to take the absolute value of the input, you better take the absolute value of the input. Or like, if you, in Haskell, if you use a view pattern, so-called, where in pattern matching you process the argument through a function, of course you do that at runtime. So I think it's no different, really. Yeah, Andy.
So, solving equations by finding their most general unifier, if you explain it to somebody, it sounds really quite easy and simple. But actually in practice, I found, and I'm sure other people find, that from a user point of view, can sometimes give you quite surprisingly general answers. So I just want to
I would love to say that I'd written a lot of verse programs. So we've, our business in life is to come up with small but very weird examples. So yes, I mean, I think the whole question, for me, a big open intellectual question, it's part of the intellectual adventure we're engaged in, is functional logic programming actually going to end up feeling like, this is the right way to write programs, or is it going to be a bridge too far? I don't know. Tim firmly believes that it is. I'm watching with a lot of interest and spending a lot of cycles trying to make it just as great as it could be. But I think it's a question that's well worth asking because it has this it's a very declarative flavor, just solve the equations. Maybe it's too general, who knows? It's something complicated to do with cognition and how people think. And yeah, I don't know. Yeah, Alan, you would probably know better than me. After all, this is your business.
Oh, good lead-in. So thinking back to our work years ago when we looked at the ways in which functional programming concepts could be made more accessible to end users by getting to think about their real values, and then we had various tricks of visualizing different universes in which those values might be different, and we did that at the time by putting, invisible spreadsheets in which the world might be different and the values would be different. I imagine that in your own mind you might have thought about whether there's a way to make the quite mathematical abstractions of verse more accessible by indicating them to end users in relation to the
because until then, all we do is wave our
just sucking the stuff out of Tim's brain and then writing it down. But how much of this is you going back and forth? How many programs have you got? No, this is easy, Tim. It should be like this.
hours on the phone. It's just 2 solid hours every week talking about denotational semantics and unification with Tim. And there's a lot of to and fro, So we spend quite a lot of time just trying to understand what he's trying to say. Then we sort of replay it back to him. And in fairness to Tim, he is thrilled with the rewrite system because until we came up with that, he thought, now I've got a way to talk about this that I didn't have before. And do you remember those contexts we had in the rewrite rules? He'd never seen that before. And so we are, iterating with him, and he is busy taking his 5,000 line C++ implementation of verse. He is re-engineering it thoroughly as we speak, because the conversations that we've had have clarified his thinking in turn. We're still not quite on the same planet. But we are getting a lot closer. But it's very much dialogue. So yes, it's a good question. It definitely isn't. What would be really interesting about verse. I hope I've given you a sense of that. And so it's an intellectual. And Tim is a kind of maverick, autodidact genius person who come up with a lot of extremely original ideas with see if it makes sense.
The execution engine, or rather, what is the basis for the rewrite rules? So I think, you said that, for instance, x equals x times x it gets stuck, even though there are solutions. So is it that the rewrite rules depend on the fact there's some discrete choice at some point to every variable, or what choices does it actually try in execution?
So I'm not quite sure how to answer that, except to say, look at the paper and look at the rewrite rules, right? And it's, if there is a rewrite rule, execute it. If there isn't, it gets stuck. But it's pretty simple. It's just unification, really. So you just do substitution. The substitution is like follow the pointers, right? And the unification is like pair equals pair, decompose the pair. That's really powerful execution mechanism. Do you have a question, somebody? Who are odd line. Alistair, we're going to stop whenever you want.
So take this one, I'll do one from online.
Yeah, okay. Yeah.
So my question is, how does negation work for unification? And my second question is, there seems to be no difference between... Sorry.
That's just a small question, isn't it? Negation is failure.
My second question is, there seems to be no difference between a sequence of choices and a list. And for example, if you do multiple indexing, so I say index array by I or j or k, does that return an array or does it return a sequence of values? There seems to be no difference.
So let me take the if you say I or j or k, that is an expression. Or I vertical bar j vertical bar k. Then you get the array of those three values. So for precisely takes this rather control flow like thing of returning a sequence of values and turns it into a data structure. And that's the thing that's like a list. So there's this funny kind of duality between choice and data structures. And what was the first question again? Negation. Right. So you can say if something. Let's say, so if you say, if E then, if E fails, you get into the else branch. So you can certainly say, if E then print it succeeded, else print it failed. So you could detect failure, you can do whatever you like. So yes, and remember, failure just means zero results. There's nothing very special about zero results in a way, right? It just means instead of 2, 1, 0. So it's a bit less discreetly spelled.
Yes. The question online was about, at the start you started off with these lovely objectives of what you wanted to try and achieve.
Yes.
You had lots of detail about the programming language.
Yes.
And have you managed to cycle back yet and check whether the program you've ended up with meets the objectives that you
not at all.
with?
So some of the objectives are put up like, usable by millions of people who haven't met each other, right, with very strong guarantees. None of that really intersects with the functional logic bit. It intersects with the type system bit, in quite a lot in a way that I didn't really articulate at all. And I didn't talk at all about transactions, which are key to... So really there's a very small intersection between those objectives and what I showed you, right, to be honest about it. But in the grand scheme of things in the project, there's a very big connection. Yeah.
Great. Well, I think we should give a round of applause to thank our... So I've got a few more extra things to do. So I think just out here we have a small present for Joyce.
No, somebody stole the present.
We've got some lovely flowers for you, Joyce. So to say... I'd also like to say a particular thank you to Joe for organising the event today. We wouldn't all be here without her organisation. Great, and so with that we then move on to tea in the atrium outside. So thank you all for coming.